Good evening. My name is K. Sanvita, and I am a first year student in Civil Engineering branch at the Institute of Aeronautical Engineering. Today, I will be presenting on the topic of random matrix analysis of spectral properties in directed complex networks. So, random matrix analysis of spectral properties in directed complex networks, which exploring the deep connections between a random matrix theory and network dynamics through spectral lens. So the intersection of random matrix science. So random matrix theory, RMT, provides a powerful mathematical framework for analyzing the spectral properties of large-scale networks. When applied to direct networks, random matrix theory, RMT, reveals fundamental patterns in eigenvalue distributions that govern network behavior and stability. So the adjacency matrix of a directed network encodes the asymmetric relationships between nodes, creating a non-Hamilton structure whose spectral properties differ fundamentally from undirected groups or graphs. So this is called as a random matrix theory and the intersection of the random matrix science. So, some spectral characteristics of directed networks are circular law, spectral radius, and eigenvalue density. So, first let us know about circular law. So, for large random directed graphs, eigenvalues asymmetrically fill a disk in the complex plane with uniform distribution, which is a phenomenon tested from the semicircular and unidirected networks, which is called as circular law. The second one is spectral radius. So the largest eigenvalue modulus determines stability and synchronization properties with critical implications for rhythmic spreading and information diffusion dynamics, which is called a spectral radius. And the third one is eigenvalue density. So the distribution of eigenvalues in complex plane reveals structural features, outliers, and indicate network hubs, while bulk statistics characterize mesoscale organizations, which is called as eigenvalue density. So some key theoretical frameworks are Guinevere ensemble, sparse network limit, and spectral stability. So the first one is Guinevere ensemble. It explains about the models of random directed networks with independent identically distributed edge weights that canonical model for non-Hermitian random matrices. The second one is sparse network limit. Analyzes networks with average degree remaining finite as network size grows, the revealing deviations from classical random matrix theory predictions. The third one is spectral stability. So it examines the perturbation theory for eigenvalues under structural changes critical for understanding network resilience. So these are the key theoretical frameworks, which are Guinevere ensemble, sparse network limit, and spectral stability. Um, Eigenvalue distribution patterns. So in eigenvalue distribution patterns, there is thing which is called complex plane analysis. So in this, the eigenvalue spectrum of directed networks exhibits consecutive patterns in complex plane. So it got some different patterns in the complex plane. So dense random networks follow the circular law with eigenvalues uniformly distributed within a disk of radius called as root n, where n is called as the average degree of a eigenvalue spectrum. So sparse networks show marketed deviations. Eigenvalues concentrate near the origin with isolated outliers corresponding to high-degree nodes or strongly connected communities. So this is basically called as a complex plane analysis where radius is root n and n is the average degree. So applications across scientific domains are of like four types: neuroscience, ecological networks, financial systems, and social networks. So matrices we use in daily life, and it is very important topic. So We basically use it in neuroscience, ecological networks, financial systems, and social networks. Like in neuroscience, analyzing spectral properties of connectives reveals organizational principles of brain networks and predicts neural dynamics from structural connectivity. So, in this way, it is used in a neuroscience technology. In ecological networks, eigenvalue analysis of food webs determines stability thresholds and identities, keystones, species critical for ecosystem resilience. So, in this way, in ecological networks also, uh, random matrix theory is used. And in financial systems, spectral methods detect system like disk in transaction networks with eigenvalue outliers signaling institutions central to financial continuation. So in financial matters also, we use random matrix theory as it is very useful. And in social networks, leading eigenvectors, identity, influential nodes, and communities, while spectral labs quantify emotion flow bottlenecks. So, in current generation, social network is a lot growing, and like the apps which are used for social networking are also developing. So, in everything, eigenvalues are used, where eigenvalues are used, and the random matrix theory is used. So, in these are the some scientific domains applications and methodological challenges and future directions. So there are four open challenges and future directions. The first one is non-Gaussian edge distributions. Second one is finite size effects, and third one is multi-layer networks, and fourth one is algorithmic efficiency. So coming to non-Gaussian edge distributions, which explains most theoretical results assume Gaussian edge weights, extending RMT, random matrix theory, to heavy tile and discrete distributions remains an active area of research with significant practical implications. And coming to finite size effects, real networks rarely reach asymptotic limits assumed by classical random matrix theory, which means RMT. Categorizing finite size corrections improves prediction for moderately sized empirical networks. The third one is multi-layer networks. Coming to multi-layer networks, spectral properties of networks with multiple interaction types require tensor-based approaches. Developing tractable RMT framework for these systems is crucial for modeling real-world complexity. The fourth one is algorithmic efficiency. So computational methods for spectral analysis must scale to networks with billions of edges. Matrix-free iterative techniques and approximate methods show promise for extreme scale applications. So these are four open challenges and future directions: non-Gaussian edge distribution, finite size effects, multi-layer networks, and algorithmic efficiency. And coming to the next one, key takeaways. What are the key takeaways of this topic? The first key takeaway is random matrix theory, bridges theory, and practice. So, random matrix theory provides a rigorous mathematical foundation for understanding spectral properties of complex networks with direct applications across scientific disciplines. The second one is eigenvalue distributions and code structure. So, the spectrum reveals hidden or organizational principles from community structure to dynamical stability, enabling prediction of network behavior from topology alone. And the third one is open frontiers await exploration. So extension to multi-layer networks, non-Gaussian systems, and finite size regimes promise new insights into the spectral properties governing real-world directed networks. So these are the three key takeaways of random matrix theory. The first one is RMT bridges theory and practice, and the second one is eigenvalue distribution and code structure, and the third one is open frontiers await exploration. So let us revise once again. The random matrix theory analysis of spectral properties in directed complex networks is about exploring the deep connections between a random matrix theory and network dynamic through spectral analysis. And here we go with the spectral characteristics of directed networks, which are three. One is circular law, second one is spectral radius, and third one is eigenvalues. And next one is the theoretical frameworks are Guinevere ensemble, sparse network limit, and spectral stability. And the third one is eigenvalue distribution patterns. We get to know about the complex plane analysis, which basically explains about the eigenvalue spectrum of directed networks, exhibit distinct patterns and complex plane. And the next one are few applications of scientific domains. And the first one is neuroscience. We use it in ecological networks, we use it in financial systems, and we also use it in social networks. And methodological advances are of four. First one is spectrum estimation. Second one is outliner detection. Third one is dynamic networks, and fourth one is weighted networks. And spectral stability of and spectral stability criteria, which is of dynamic networks. So it basically explains the synchronization and coupled oscillator networks, which is depending on the eigenvalue gap, with larger gaps facilitating global coherence. The spectral radius rho of A of the adjacent matrix determines linear stability systems with the rho of A is less than 1, which converts to equilibrium, while rho of A is greater than 1, which indicates instability or chaotic behavior. And the open challenges and future detections are of four. First one is non-Gaussian edge distribution. Second one is finite size effects. Third one is multi-layer networks. And the fourth one is algorithmic efficiency. And what are the key takeaways? Three. First one is random matrix theory bridges theory and practice. Second one is eigenvalue distributions and code structure. And third one is open frontiers